Good afternoon, everyone. Let's get started again. Right, before, this was the last slide I showed before lunch, and it's on drain analysis. Now, the question is, in a drain analysis, just to recap, in a drain analysis, there is no issue about the pore pressure because the pore pressure is separately calculated. It's well known. If it's hydrostatic, it's known. If it's not, it is calculated either by seepage consideration or something like that. So whatever it is, the finite element doesn't have to calculate the pore water pressure. It's already known. Okay. So basically, from the point of view of computation, the seepage analysis is actually quite straightforward to compute. Now, the next question is, what about the undrain analysis? The undrain analysis is always the tricky business in terms of trying to figure out what the program is doing, because especially when you are specifying a set of what we call effective stress parameters. That means like E dash, nu dash, K dash, G. These are effective stress parameters. So the question then is, how does the program work out the stress strain matrix? Because at the end of the day, in finite element analysis, equilibrium is still enforced in terms of total stress. Equilibrium is still enforced in total stress. You cannot ignore the effect of the pore pressure on the equilibrium of the soil. It is all taken into account. So there has to be a way of transforming the total stress, the effective stress strain matrix into a total stress strain matrix, into something that include the effect of the pore water, okay? And the transformation in essence involved doing this. Supposing you put in effective stress parameters like E dash and nu dash, then the question is, the program will be able to obviously calculate K dash or bulk modulus and shear modulus. That's no problem. That's direct. Then what about the total stress? What about the total bulk modulus? The total shear modulus is also straightforward. It's just equal to the effective shear modulus. Because shear modulus is not affected by what? It's the bulk modulus that is the question. How does the total bulk modulus relate to the effective bulk modulus? So this is where the program has to calculate the thing itself. And what it does, I won't go through the mathematics because there is like 2 to 3 slides of mathematics. But essentially, the upshot, the conclusion of the mathematics basically says that if you have done all this mathematics, the result of the mathematics basically says that the total bulk modulus is equal to the effective bulk modulus plus the modulus of water. This is the modulus of water. Kw is the modulus of water divided by N, where N is the porosity of the soil. So it is equals to the total bulk modulus is equal to the effective bulk modulus plus the bulk modulus of water divided by the porosity of the soil. Divided by the porosity. Now, this is where the trick comes in. And you may say, hey, how does that change the whole thing? The way it changed the whole thing is this. And that is that in most soil, the bulk modulus of water is much higher than the effective bulk modulus. Because water is much less compressible than soil. So the bulk modulus of water is much higher. Kw is much higher than K dash. Kw is much higher than K dash. So basically, what happened is that as a result of that, what effectively happens is that K, the total bulk modulus, shoot up, increase quite a lot. But the shear modulus, the total shear modulus, is the same as the effective shear modulus, and there's no change. Is that all right? So effectively, what the program actually does, when you take that into account, the total stress strain matrix in terms of effective stress parameters, the total stress strain matrix is this. And you can see this is K dash, the effective bulk modulus. K dash, effective bulk modulus. This G dash, in fact, is the same as G, so no difference. But what you get is an additional term in all this. This is the bulk modulus of water divided by N. The bulk modulus of water divided by N. Bulk modulus of water. Now, this is the typical approach used by, I would say, most geotechnical program, including Plexis, GeoF, EA, SageCrisp, whatever, they use this method of doing. So what you do is, when you enter it in, you are entering effective stress parameter. The program will then add on the bulk modulus of water to it. In fact, the program doesn't even add on the bulk modulus of water. It adds on a very big number that simulates the bulk modulus of water. But it's not necessarily equal to the bulk modulus of water. It can be the bulk modulus of water, but usually all you need is a number, all that is required of this number, kW over N. This big set of terms here, kW over N, all that is required is that it is much bigger than K dash. Typically 1,000 times, maybe 10,000 times. Okay, in some version of Plexis, they set this to 100 times. This equals to 100 times this. And you can easily see the error when you run Plexis. In a consolidation analysis, when you start with an undrained situation, you put on 200 kilopascal of surcharge on the soil in the undrained analysis. What appears in the pore water pressure is 198 kilopascal. So 2 kilopascal is missing because it's carried by the soil skeleton. And that happens because the program doesn't specify a high enough bulk modulus of water. If you want it to be totally incompressible, it should be infinitely high. So you want it to be reasonably high. And typically, I recommend to people, if you have to specify, you specify something like 1,000 times higher than the bulk modulus of the soil. Okay, but these days, a lot of programs, they are intelligent enough, they look at the soil property, they will know how to prescribe something that is about that order of magnitude higher. So you don't have to worry. So in fact, this thing is something you need not to worry about because the program will typically take care of it for you. It is sometimes when you end up with some program that is not able to set it high enough, sometimes you may get some funny results. So when you get some funny result, one of the things you want to look at if you are doing undrained analysis is check whether the program set the bulk modulus of water sufficiently high compared to that of the soil. So that is one of the things that you need to take care of. So essentially, what happens is that all that is required is you have something that is much higher than the effective bulk modulus of the soil. So basically, you have put in effective stress parameter. The program add on a very big term to some of the coefficients, some of the entries in that matrix, and what comes out looks like a total stress strain matrix. Is that all right? So this is how the total stress strain matrix is generated. And the effect of this is in essence similar to doing a total stress analysis with a Poisson ratio of 0.4999 or something like that. Because that prescribes incompressibility. When you add a very high number over here, in terms of the bulk modulus of water divided by porosity, you are also prescribing incompressibility. You are also, in another way, prescribing incompressibility. So the two ways are just different ways of prescribing incompressibility. Is that okay so far? This is how programs like Plexis. So some of you may wonder, hey, I put in effective stress parameter. Should I be using EU and nu? No need. There's no need. Just put in E dash and nu dash. You follow? It will calculate it for you. Now, so the question that comes out is this. You can do a total stress, you can do an undrained analysis by specifying effective stress parameter, and the effective stress parameters are K dash and G, and the program automatically adds something in for you to make this material look nearly incompressible. So then you have an undrained situation. Now, there is, as I mentioned earlier just now this morning, another way to conduct an undrained analysis, and that is in terms of total stress. And this is how a lot of the older softwares, I don't know anyone except for XCAF, which Wong Kai Sin in NTU used to sell. They work in EU and nu, total stress, undrained modulus, and undrained Poisson's ratio. And in total stress, what they do is that you only have to specify EU, and nu is something that you can put a number that is just close to 0.5, or sometimes the program will just choose it for you. Okay, so the question is, which one should you use? What is the advantage and disadvantage of doing this method, both methods. Okay, the first method requires you to enter two parameters, k dash and g, or e dash and nu. And nu is not 0.449, nu dash is not 0.49, it's maybe 0.2, 0.3, 0.35, something. So you have to, and it's probably not the easiest thing to measure in the world, so you have to sort of guess a number, 0.3. But the nice thing is that the range is not that wide. 0.35 to 0.25 to 0.35 is the kind of usual range for soil. So anyway, so you need to enter two parameters. With the second method, which is the total stress analysis, okay, in Plexis we call this method C, total stress analysis. You only need one parameter, and that is EU, because nu u is 0.49 or 0.499. So basically, the disadvantage of using the effective stress approach is that you need to enter one more parameter, which you either guess or you do something. You just, the second method requires you to use one less parameter. However, the first method is used in most modern geotechnical software because you can, in an effective stress analysis, you have the effective stress strain matrix, which then allow you, after you've done everything, the program will actually be able to calculate the effective stress changes for you and the effective stresses. So once the program can calculate effective stress, it already knows the total stress. Total stress minus effective stress is pore pressure. So the program can actually produce the pore pressure for you. If you use the second method, which is the total stress method, you will not be able to calculate effective stress. You only get a total stress. You will not know effective stress, and you will not know the pore water pressure. So that is the disadvantage. The disadvantage is that you do not know the effective stress and the pore pressure separately. You only know the total stress. Okay, so it depends on what you want to know. Some people, structural engineer actually likes the second method. I know in Singapore, there were a few structures. I mean, it's a bit like religion, whether you want this religion or that religion. Some they think of it like a religion. So they said the effective stress religion or the total stress religion. But of course, in soil mechanics, we always believe in the effective stress religion, or that's what we think we like to believe. So anyway, that is the situation. So in an effective stress analysis, you can always calculate the effective stress and pore water pressure. The question is, can you use Plexis or GeoFEA or some other software to do the second method? Of course you can. Of course you can. And there are ways you can do it. Oh, I haven't come down to it. Maybe tomorrow but you can do it in Plexis. If you want to do a total stress analysis, you can always do it because you assign E to EU, you assign nu to 0.49. I think you turn on the non-porous. The moment you turn on the non-porous, it won't compute the pore pressure for you. So you won't see it. And even if you don't turn on, what you do is this. The way you do it, for example, in programs like GeoFEA, you can do the same thing by assigning E to EU, nu to 0.49. Okay? And then what happens is that you treat it as a drain analysis. Then all the pore water pressure that come out will look like zero, or there's no change. But in fact, it's has no effect at all. That pore pressure has no effect. What it means is that you are not actually seeing the pore water pressure. You are just seeing the effective stress is the total stress. That's all. Is that all right? So you can either do one or the other method in most software if you know how to change the parameter in a sensible way. You can use an effective stress program to run total stress analysis. On the other hand, you cannot use a total stress program to run effective stress analysis because it doesn't accept effective stress parameters. It will not separately calculate the pore water pressure for you. You will take all your entry to be total stress entry. Plexis is an effective stress program. So you can actually put in total stress parameter and actually get total stress only out of Plexis. No pore water pressure, no effective stress. It can be done by setting E equals to EU and nu equals to 0.49 and turning on the non-porous. So this is how you would do it if you have a software like Plexis. So it's not that you cannot do it, it's just that you just get a bit less result to play with. And you can see sometimes in some cases, people are interested or they are concerned about pore water pressure, in which case then you have no choice but to use effective stress program. But the other thing is, of course, if you want to run very sophisticated model, anything more than a more Coulomb, they are almost always expressed in terms of effective stress. Okay, more Coulomb, there are effective stress and total stress version, but anything more complicated than that is always in effective stress. So when you use something that is more complicated, like the chem clay or the Plexi soft soil model or the hardening soil model, they are all expressed in effective stress. So you have no choice then to use other than to use effective stress analysis. So these are some of the things. So the total stress analysis does not usually work well, except for very simple soil models. Okay, I finished off the part on drain and undrain, and the next part is something. Can I just have a show of hand? How many of you have learned about stress path before? Good. At least some of you have some contact with stress path. Okay, but how many of you have not heard of stress path? It's okay, don't worry. I just want to find out how fast or how slow I should be going. How many? Okay, we'll just have to go a bit slow just to make sure that you're.
Unconfined compression.
You all right?
So, with this report in hand, majority of the projects which we see in this part of the world is, you can't use anything more than,
Yeah, I appreciate your question. I think that what you're telling me was the situation. No, I mean, really, it's a question of, I would say a disconnect, not the disconnect, but a lag between what is needed in the technology and what the industry is doing at the moment. And this gap was very obvious in Singapore. When we first, I can tell you, we have exactly the same experience. Back in 1990s when we first started using FEM, every soil investigation report is nothing but SPT. UU test. UU test. You can't get anything out of it. It's just basically CU. There's no C dash, V dash, nothing, And when you ask people to do CIU test or consolidated undrained test, consolidated drain test, they look at you like, oh, this guy is talking Martian, I mean, this is what, but these days, actually things are starting, but in a sense, it is an evolutionary change. It's not something that will take place overnight. You alone, definitely, you go and talk to them, they will not bother. But if there are a lot of people coming to the soil investigation company and say, hey, we need this test, then the soil investigation company will one day wake up to the idea that I can actually make some money doing this kind of test. And then they will start doing the test. And then you will start seeing soil report. And then you start seeing stress path. I mean, like just now I showed you that stress path. This is not something that's done for research. This was in a report dating back to 2004. I saw for the Fort Canning Tunnel. It's a 16-meter diameter tunnel done using the new Austrian tunneling method. We did the analysis for it. It was a 3-dimensional FEM and a very sophisticated. We actually put in 4 poling, simulate the 4 poling, simulate even the hardening of the shotcrete. It was done on abacus, okay? Because only abacus has the flexibility for it. So, and this is a soil report that this is a stress path, a set of stress paths that appeared in the soil report. But year after year, I will produce this soil report in class, and I will ask all the students, many of whom are practicing engineers. I said, do you know how to use that thing there? And everybody looked at me like, what the hell is this thing, You know what I mean? So basically, what it means is that, obviously, somebody, if you say, I need to do this particular test and get this report out, if you tell them, I will only pay you if you get this report out, or I pay you a lot more if you get this report, this graph for me, they will do it for you, But it is not something you can get going in one night or 2 days. That kind of thing. It's something that will take years to happen. And there has to be a sustained request coming over and over and over again. Then they will start to do it well. I mean, this is the reality of the situation. So it's not your fault, but it's just the fact that the industry hasn't got got around to it. So for those of you, for example, if you say the only thing you have is an SPT, obviously the SPT cannot allow you to get C dash and V dash. There's no way you can do it. All right. So basically, the only thing you can hope to get from the SPT is CU. Right? That's the most commonsensical thing. Then people will say, okay, what do I do? Well, one thing to do is it probably will not be as accurate. You probably have to look up some of the papers written, because certain soils in India are quite well known. You know, like black cotton soil and all that. They're quite well known. So there may be some people who have written up some numbers somewhere. And this is how we usually do it. The only thing is that in Singapore, we are somewhat more fortunate, because when they built the MRT, they actually did a very detailed studies of all the major soil formation. And there are a few reports that come out, the likes of which I've never seen elsewhere in the world. It's a huge collection of things telling you even the Skempton pore pressure parameter, how it actually varies from what range to what range. And this to me is incredible data collection. This is very good. And that was back in the 1985. But of course, you ask me how many people use that, I'll say probably very few ever used it. So, but for those people who know how to utilize this, this is a very rich reservoir of information that you can tap upon. So if you don't have, if your soil report is really very minimal, bare minimum, and you can't do anything, then the only thing you can do is to look at the literature and see whether anyone has done something similar. You know, but usually it all have to start with government projects, because government project is big. So the government client can actually say, I want this and this and this and this. And I tell you, there will be somewhere in the country, there will be some SI company that will go and do it. If they are paid enough, you pay them enough, they will do it. So if you don't pay them enough, they'll look at you and say, what is this consolidated undrain test? You know, or consolidated drain test. But if you pay them enough and you say, these days they are quite, I think we are a bit more fortunate, because there's a lab testing scheme, accreditation scheme in Singapore. So when they set up a lab, they have to be accredited to either the British standard or the ASTM standard or both. So basically, we can even tell them, I want you to do a consolidated undrain test according, in the past it used to be BS 1377, and then it's the ISO 17 something 98 or something like that. So you can tell them, I want you to do according to this standard, and they will do it for you, because they are accredited to that particular standard. So this is something that I think government clients can actually influence the situation. But if there is not enough big jobs to go around, then I think it will probably be a bit slow doing it. This is my experience from Singapore. But Singapore is a small country. It's easy to turn a small ship around. Harder to turn a big warship around, big battleship, aircraft carrier, hard to turn it. So I don't have a solution for you. All I'm telling you is that your experience is is similar to what we used to have. So I can empathize with your situation. The only thing I can tell you is look at what the researchers, because researchers probably have measured a few things here and there. And all it takes is someone to sort of collect all this data together. You know?
That's what we do.
Yeah.
But it's a good thing to say to tap the MRT projects, because we have
Yeah.
Bombay, Metro Delhi, and I've seen the geotechnicals that are hidden in deep cupboards.
Are they okay?
They've done it, some
Yeah, so somebody should actually take that report out and actually publish that.
someone should actually
Yeah.
tap
Yeah.
this. It's a big resource.
Yeah, it's a big resource. I mean, I used to give it to my student. I think I even have a PDF copy of the Singapore reports. You know? Yeah. But what it actually needs, actually sometimes it's ironical. You need a disaster, like the Nickel Highway, to wake people up. And then, we better do things properly. Otherwise, things will just carry on as usual. You know? In Singapore, things was carrying on as usual until something collapsed, and then everybody woke up, and then the minister said we have to do things. And then when the minister said we have to do things, everybody else will say we have to do things. So it's like that. That's the way it works. It's all top down. So I hope it kind of, I don't think I will answer your question. I think I'll probably just say that we have similar situation, and this is how we sort of got around the situation. God. But you're right, even today in Singapore, a lot of the very small projects, especially those whom the clients are very small, foundation projects, 5 to 6 boreholes, they're not going to do any CIU tests, They're not going to do that. So they will just, so now someone is setting up a big data bank of soil test results in Singapore, soil properties. So once it's ready, then it'll be open to public. Yeah, sorry. Yeah. So once it's ready, it'll be open to public. I think someone should do something similar for something like Bombay. Then you can start from there. Okay, anything else? Okay, now the next part of the thing is about stress path parameters. And I will introduce stress path in a very simple, what I think is a very simple, because actually stress path can scare people. A lot of engineers in Singapore, when you tell them stress path, they got scared off because, what is this thing? It's something very mysterious and very hard to understand, but actually the idea is very straightforward. Okay, where you already know that in order to get a complete description of the state of stress in a 3-dimensional medium, you need 6 stress components, right? You need 6 stress components. Now, very often, you want to see, because in FEM, you're looking at simulation, how the thing changes during the event, some event. The event could be when you're excavating a tunnel, that's an event. Excavating the soil, loading a power foundation, that is also another event. So essentially, you want to see how the stress changes over the course of an event. And that event could be an excavation sequence or a loading sequence or something like that. So basically, the idea is how you may want to express or study how the stress changes over the course of the event. And this can be done by plotting stress path. Okay? Now, stress path plot is nothing more than a plot of one stress component or parameter against another stress component. Okay? There is a very simple way of visualizing stress path. Okay? Is to look at the changes to a Morse circle in the triaxial test. Do you remember the triaxial test? Okay, I'll just show the triaxial test again. This is a classic triaxial test photograph and a picture, and you can see the soil sample. The triaxial test is nothing more than a compression test. It's the soil sample. In fact, the idea is to just compress the soil sample until it fails. Okay, the thing that is non-standard about the triaxial test that you don't see in a lot of structural testing is the fact that there is facility to apply confining pressure or radial stress to the soil skeleton, to the soil specimen. And the reason is because it has been found that soil is stress dependent, the behavior of soil. So you want to apply a lateral pressure to change the stress so that you are able to control the behavior of the soil, so to speak. So in order to do that, you need a rubber membrane, a rubber membrane. And then this is the loading ramp that applies the load, okay? And you would have various openings for you to allow you to measure the pore water pressure, to control the pore water pressure, to set the pore water pressure in a drain test, or to measure the pore water pressure in an undrained test, and so on and so forth. But essentially, it is nothing more than a cylindrical specimen which you squeeze to death. All right, axially. So this is essentially what the triaxial test is all about. Now, you will remember that when we do a triaxial test, one of the things that we always plot is a Morse circle. Okay, and in a triaxial test, there are 2 stresses that are obviously important. The first is, let's take a compression test first. A compression test, the vertical stress is also the major principal stress, right? The lateral stress is also usually the minor principal stress, and there's no shear stress. All right, so there's only sigma 1, sigma 3. All right, sigma 1, sigma 3. Or if you like axial stress, sigma A, sigma R. Sigma R is the radial stress. So if you start with a triaxial test, at the start of the triaxial test, everything is, let's go back to the thing. Everything is isotropic. There's no load coming in, So when you pump up the water pressure inside the triaxial chamber, what happens is that the water pressure will be applying an all-round stress onto the soil specimen, all round. So the stress is totally isotropic. At that point of time, at the start of the test, the Morse circle is really just one dot. just one dot. So it starts here, one dot. Because the major principal stress is equals to the minor principal stress. The major principal stress is equal to, so the two are coincident. The diameter of the Mohr circle is 0. Correct? Is zero. So basically, you will start off as a dot, and then as you increase the ram load, the major principal stress will increase, but the minor principal stress will stay the same. And so the major principal stress will move out in this direction, and as it moves out, the Mohr circle gets bigger and bigger and bigger. Correct? While the minor principal stress stays the same. This is a typical cause of event in a triaxial test. Now, of course, you can say, I can plot a whole series of circles to represent the stress changes. But you realize that, in fact, in a triaxial test, the number of Mohr circles you can plot is infinite. Because there's infinite number of stress states as thing changes, depending on how fine you want to cut it. Right? And usually, in conventional testing, the circle we plot only is the last circle at the point of failure. So when we plot the triaxial test Mohr circle in a standard laboratory soil test report, it is actually the Mohr circle at failure. It is the Mohr circle. That's the only circle. But there are actually an infinite number of other Mohr circles in the middle of the test that has not been plotted. So if you plot everything, it will be quite messy. And you can see it's a black mess. So you can't see where the test is going. Okay? But there is a way to do this in a simple way. And the simple way is to say, look, instead of plotting the whole circle, why don't we just, for each state of the test, each Mohr circle, we just plot one point. The point is the crown. We just plot the crown. Not the whole circle, just the crown. Okay? If you plot the point in the crown, then as the circle expands, the crown will start to move up in this manner. And so it will trace out a path. This path is really a stress path. Because it tells you how the Mohr circle is changing by just plotting one point, the point of the crown. Okay? The way to plot it then, if you want to do it, is to say, okay, I just plot the crown of each circle, and as the test progresses, I trace out the path of the crown, traces out a path that you might call a stress path. And this is one version of the stress path. Okay? Like I say here, one is to just plot out the path traced out by the crown. And so in a triaxial test, you can easily write it out very simply. The major principal stress is the axial stress in the typical triaxial test. The minor principal stress is the radial stress. Agree? Okay. The coordinate of the top point of the Mohr circle, which is the crown, can therefore be expressed as follows. The x coordinate, we call it S, is equals to sigma 1 plus sigma 3 over 2, the average of the two, which is the center of the circle, is actually the coordinate of the center of the circle. Alright, the y coordinate is actually the radius of the Mohr circle. Correct? Sigma 1 minus sigma 3 over 2. And so therefore, this set of coordinate S and T describe the stress path, and they are called stress path parameter. And indeed, they have been used by Bill Lamb, Whitman, Bob Whitman, Chuck Ladd, and etc., all their researchers in MIT. And I will just call them MIT stress path parameters. MIT stress path parameters. Now, the MIT stress path parameter is still very commonly used in practice. But for the purpose of describing constitutive model, they are not so commonly used, except possibly in MIT constitutive model, the kind of model that Andrew Whittle came out with. But it's not so common. You don't usually find those models around, so I don't think you need to worry too much about them. But essentially, this is one form of a stress path parameters. Okay, and I will term them as MIT stress path parameters. So you can refer to them also as MIT stress path parameters, and the parameter are S and T. Okay. Now you can also express them in incremental form. That means not in total. That means in changes. So changes in S, change in S equals to half of change in sigma 1, delta change in sigma 1 plus change in sigma 3. Change in T is equal to half of change in sigma 1 minus change in sigma 3. And similarly for effective stress path parameters. Similarly, for effective stress path parameters. Okay, now, okay, I'll just give you one example, and actually I didn't want to go into this example in detail, but and this is a hint, but because of the assessment and all that sort of thing, I thought I better do something. Okay, and I think you all got the message. Anyway, this is a very simple thing. The first thing is this is just to illustrate to you how you can calculate, how you can deduce stress path. The simplest way to deduce stress path is to consider the change, because a lot of stress path changes are actually quite simple. Okay, now let's take a case of an example in which you have a triaxial test. In a triaxial compression test, only the axial load is increasing, right? The radial stress, which is the cell pressure, is constant. So immediately we can say in total stress, delta sigma 3 is 0. There's no change in sigma 3, correct? So there's only change in sigma 1. Then if you look at this, then delta S is equal to half of delta sigma 1 because this is 0. Delta T is also equal to half of delta sigma 1. So in other words, delta S equals to delta T. Or delta S over delta T is equals to 1. Which means that you suddenly end up with this condition that the total stress path can be deduced by setting delta sigma 3 equals to 0, which leads you to this delta T over delta S equals to 1. Now, you just imagine a plot of T versus S. And now I tell you that the change in T is the same as the change in S. That is, a gradient of the plot is always 1. It's obviously a straight line with a gradient of 1. So it's just nothing more than a straight line with a gradient of 1. So essentially, the total stress path is a stress path with a gradient of 1. So the general approach, the usual approach to deducing stress path, okay, I would say it worked 95% of the time, if not 99% of the time, okay, is to just consider change in the two parameters and at what rate are they related to each other. That's all you need to do. You don't have to go integrating and do all kind of funny things. Just consider the change. Is that all right? Okay. So that is the simple way of doing it. Now, you can also obtain the effective stress path, which is a bit more tricky because in order to get the effective stress path, you need to know how the pore pressure is generated. Okay. Now, I will skip ahead a little bit and talk about Skempton's pore pressure parameter. How many of you have heard of Skempton's pore pressure? Have done Skempton? Oh, I think most of you have done it. Okay. Yeah. I think that is the thing, because I think in your undergraduate there's still a requirement, right? Skempton's pore pressure parameter. Yeah. Because I know that in certain countries they are not so strong. But I think in India you still have a strong British influence in your education system. I think so. The British is still there. And there's one thing there's the sense of rigor there. Because a lot of my Chinese students don't understand what is Skempton's pore pressure parameter. You tell them, they look at you like, what the hell is this? But I think you all know. Okay, so Skempton basically was I think he may be the first, Cooling was the first lecturer in Imperial College. I think Skempton was the first full professor, okay, in Imperial College, in soil mechanics. And he was the guy who contributed a lot to the development of soil mechanics, to Imperial College being one of the centers of soil mechanics even now, one of the centers of soil mechanics. Okay, Skempton basically tries to describe excess pore pressure generation in terms of changes in the total stress. He doesn't want to describe it in terms of effective stress, because you only know the changes in the total stress. You don't know the changes in the effective stress. You want the excess pore pressure generation. And the Skempton's pore pressure parameter, Skempton's pore pressure equation, can I use the board? The Skempton's pore pressure equation just simply says this. This is the Skempton's pore pressure equation. And there are two parameters. There's an A and B parameter. These parameters are determined experimentally. Now, basically, Skempton says that you can relate pore pressure changes in an undrained test to the changes in the minor principal stress and the major principal stress by the use of two parameters, A and B. Now, it turned out that B, it can be calculated in principle, theoretically, for a saturated specimen. And for a saturated specimen, B is equals to 1. B is equals to 1. And so, one of the usual tests of goodness, the test of goodness of an undrained or drained triaxial test after console, and is the degree of saturation, right? You want to ensure close to full, is to check the B value, to get the soil lab to test for the B value. And so, and there are specifications in the BS 1377, the B value should be, I think, be 0.96 or 0.95 or higher, something reasonably close to 1, before you can accept that set of test results. So B is in a sense, there is a theoretical limit of 1. Okay, A is a parameter that is more variable and depending on the soil property. Okay, depending on the soil property, and it can be shown A is equals to 1/3 for a linear elastic material. A equals to 1/3 for a linear elastic parameter. Okay, so if B equals to 1 and A equals to 1/3, then the Skempton's pore pressure parameter equation can be written as this, because the B disappears and the A becomes 1/3. And so then you get a measure of, you get an expression of the excess pore water pressure in terms of change in sigma 3 and change in sigma 1. Alright? Then what you do is you calculate what is the change in the major principal effective stress. Effective principal stress, delta sigma 1 3. So delta sigma 1 dash. Okay? Delta sigma 1 dash is equals to delta sigma 1 minus the excess pore water pressure. Delta sigma 1 minus delta U. And after you have done all this, substitute this guy in, you end up with this. And you realize that this is 2 delta T. Because delta T is half of this. So this is, delta T is half of this thing. So this is 2 delta T. 2 delta T multiplied by 2/3 is 4/3 delta T. Okay? Similarly, you can show that delta sigma 3 dash is equals to minus 2/3 of delta T. Minus 2/3 of delta T. Okay? So you can then, based on delta sigma 1 dash and delta sigma 3 dash, calculate what is delta S dash. Okay? Which is equals to delta T over 3. And delta T over delta S dash is delta T divided by delta T over 3. And so the result is that delta T over delta S dash, which is the gradient of the slope of the effective stress path, is 3. Is that alright? So delta T, this simple calculation just basically shows you how you deduce the slope, the gradient of the stress path. The first one is a very direct calculation. First one is a very direct calculation. The other one involves a bit of pore pressure and substituting, but really nothing more than a simple set of algebraic maneuvering, and you will be able to get the total and the effective stress path. So if you plot out the total and the effective stress path, it actually looks like this. The total stress path is the red line, has a gradient of 1 to 1. The effective stress path has a gradient of 3 to 1. And you can see that I have purposely introduced an offset at the start. And this offset at the start is the pore pressure that you set at the start of the test, which is usually a high enough pore pressure to ensure that the specimen is saturated. So basically, this is what we usually call the back pressure. This is the back pressure that you use for the triaxial test. Now the back pressure is ignored in some of the stress path plot. Although I put it here explicitly, in some cases, very often you can ignore it because it doesn't affect the behavior. Okay? Doesn't affect the interpretation. Sorry? Yeah. Which one? This one. This one. Is that right? Oh, you're asking why this is not delta T dash. Okay. I forgot to tell you that. Okay. I'll just write it out. Can you see the board? We don't want to switch on the light, but can you see? Okay. Delta T dash equals to half of delta sigma 1 dash minus delta sigma 3 dash. Agree? according to the thing. But this is delta sigma 1 minus delta U. This is delta sigma 3 minus delta sigma U. Delta U. You see? Okay. Now, actually, in a physical way, it's very easy to explain. Because what is T? T is the radius of the Mohr circle. If you ever plot the total stress Mohr circle and the effective stress Mohr circle, you will see that they all have the same size, both of them. The two corresponding Mohr circles must have the same size. If they don't have the same size, something is wrong with the calculation. They have got to have the same size. So the radius has got to be the same. The two circles are offset by the amount equal to the pore water pressure, but the size must be the same. And it all has to do with the fact that the radius of the Mohr circle is the largest shear stress the sample is experiencing. And we all know water cannot carry shear stress. So total shear stress is the same as effective shear stress. Correct? Anything related to the size of the Mohr circle has some relation to the shear stress. That's why in an isotropic stress situation, there's no shear stress. Mohr circle is a dot. See? That's why it's all related. So the delta, we don't usually use delta T dash. We just say delta T. And it's understood to be the same as delta T dash. And whether you calculate delta T dash using this part or using this part, the answer should be exactly the same. Should be exactly the same. Is that okay? Okay, so you can see these are the typical total and effective stress path. Now, this is a set of stress path. Now, you can actually see the total stress path. When you look at something, this is probably something that was generated by some computer program. All right, and I'm not sure whether the guy who generated it also know what it means. But anyway, it's a standard thing. You press a button and everything comes out, So this straight away go into a report. So this is what you get. But anyway, it does look like someone who programmed the computer knows that it may be useful. Anyway, the two axes. The two axes represent, instead of T, he used Q. But we won't use Q because we reserve Q for something else. Half of sigma 1 minus sigma 3. Okay? P and P dash is actually S and S dash. Is equals to half of sigma 1 plus sigma 3, or half of sigma 1 dash plus sigma 3 dash. Is that alright? So, the question is that this is a double plot. On the x-axis, you're plotting S and S dash. On the y-axis, of course, there's only T. There's T and T dash is the same. Alright? So basically, the first thing to interpret is to separate the total stress path from the effective stress path. And there are three sets of test results over here. Each set of test results consists of one total stress and one effective stress path. And the total stress path, the way you want to look, one of the first thing that will distinguish you is this. The total stress path is usually very nice because it's controlled by the guy doing the test. The total stress is controlled. You want the total stress to occur in certain way, monotonic testing, that's what you see. And so it's a very nice straight line. And all these three are very nice straight line, all the way going up. This one, there's one. And these are all having gradient of 1 to 1. They are parallel to each other. And so that's the three total stress. All right. The effective stress is the other set of three lines. This has a gradient of 3 to 1, 3 to 1, 3 to 1. And right at the start, you can see just a little bit of 3 to 1, then it bend over. Okay. So these three are actually the effective stress path. Now, you might ask, why is it that the effective stress path start off so nicely and then suddenly it just shoot over? Because the guy yielded. So you can see actually the yielding is very clear. It is very nicely elastic up to around the line of failure, the failure envelope, and then it just suddenly switch over. It just turned around. And the reason is because yielding has occurred. The moment it yielded, the stress path is no longer, the effective stress path is no longer 3 to 1. It's no longer linear elastic. So in fact, it's a very nice way to tell whether your failure envelope is correctly drawn in certain situations. So it can be very, very sharp. It's much sharper typically than the stress-strain curve, drawing stress versus strain. Because a lot of the time the stress-strain curve is very rounded. So you don't know exactly where the yielding takes place, here or here or here or further up. You don't know. But when you plot, sometimes when you plot things like this, it is very sharp and you can actually pick up the yield point quite nicely. Okay, so for example, in the third specimen, you can see the yielding occurs around here, which is just over 100 kPa, 110 or whatever it is kilopascal. Okay, that is at half of at the radius of the Mohr circle is just over 100 kilopascal. And you can then deduce how big the Mohr circle is. Is that all right? And the x-axis will tell you what is the location of the center of the Mohr circle. So you can actually draw the Mohr circle at failure, deduce the Mohr circle at failure. Is that all right? So therefore, actually you can read the stress path like this. You can actually do a bit of counter-checking on whether the guy who draw the failure envelope give you the angle of friction has been diligent or not so diligent. Okay. Okay. So anyway, these are some examples of how you can use the MIT stress path. The MIT stress path is quite often used in practice, but I want to go through a second. I will skip this part here on this undrain test on linear elasticity. It's a bit more complicated, so I think I'll let you to look at the mathematics, and if there's any question, we can discuss it tomorrow. So basically, this is just another example of stress path, okay? But a more complex example. So basically, the idea is this is the two are the same. That one, the previous slide gives the mathematics. This gives just the conclusion, and the conclusion is that if you have a plane strain block like this, and you do a compression where there's no shear stress, just do compression vertical and horizontal, the effective stress path will be a vertical straight line, and the total stress path is still a straight line with a gradient of 1 to 1. And basically, the previous slide shows you why that is the case. That is the previous set of mathematics. Okay. So you can take a look at it at your own time, and if you have any question, we can always discuss it tomorrow. Apart from the MIT stress path parameter, it turns out that there is another set of stress path parameter that's more often used in constitutive modeling. And that's the reason why we have to do it, because this course is about constitutive modeling. So you have to be able to express the model in terms of that alternative set of stress path. Okay? And the alternative set of stress path is founded on two alternative parameters, which I will just call P and Q. Again, I will not go through the detailed mathematics. Okay? I will not go through the detailed mathematics. I will just run quickly through the notion of P and Q. The P is very easy to explain. The Q is very hard to explain. Okay? But you can actually see it in a physical sense. So I rather than to go through the mathematics, which I have on the slides, I have it all on the slides, I have all the mathematics, but I will focus more on finding a relationship between all these stress paths. What are their relationships? That is important to you rather than to try to remember all the mathematics. Okay? Now, the first way of calculating the first stress path parameter is P. And P can be easily understood by looking at the volumetric strain. You remember the volumetric strain epsilon V is equals to the sum of the three normal strains. Correct? And from the three equations of the generalized Fook's law that we dealt with earlier this morning, you can relate these three, the sum of these three, to the sum of the three normal stress. Okay, you can easily show that it's equals to this based on those three equations. And the three equations that I was referring to are this. Right at the start, the three equations. These three equations. 22 to 24. You just add up everything on the left-hand side, and then that is equals to everything on the right-hand side added up. All right? And then you will get something that looks like that. Okay? Now, you know that K is equals to E over 3 into 1 minus 2 nu. That is one of the earlier equations we got. E over 2 into 1 minus 2. So you can actually relate this, convert this. Instead of E, we can express it in terms of the bulk modulus K. The bulk modulus K. And it turns out looking in a very simple way, the sum of the three normal stresses divided by 3K but we choose to split it this way. The sum of the 3 normal stresses divided by 3, then divided by K. Sum of the 3 normal stresses divided by 3 is actually the average normal stress, correct? Which we call the mean normal stress. So the mean normal stress, so basically what it says here is the volumetric strain is equal to the mean normal stress divided by the bulk modulus. That's basically all there is. Okay, so the mean normal stress can be used as one stress path parameter. So one of the stress path parameter is the mean normal stress. Okay, so P equals to this is one of the stress path parameter, and it is related directly to the volumetric strain. And in incremental form, you can express it as this: change in volumetric strain equals to change in P divided by K. So this is how you can actually express it. So P is one of the stress path parameter. Now there's a nice thing about using P. The nice thing about using P is this, that if you talk in terms of a single stress component like sigma x, sigma y, or sigma z, or sigma, a general sigma, when you talk about sigma, the first question that somebody may ask is, sigma on which plane? Because even at a point, if you rotate the plane in different direction, the normal stress can change. So there is a directional quantity, directional characteristics to the normal stress. On the other hand, if you look at P is only related to the volumetric strain. And the nice thing about the volumetric strain is that it has no directional quantity. It's just change in volume divided by volume. So there's no directional quality in there. So therefore there's only one P. When you talk about mean effective stress or mean normal stress, you don't have to say in which direction. In fact, you can easily show that if you take the normal stress acting in 3 orthogonal directions at a mutually right angle, you take the average of those 3 normal stress. No matter which direction you choose, how you rotate it, it is always the same. It is always, that is the one quality that it has that is nice. So when we talk about mean normal stress, we never talk about direction. There's no need to talk about direction. Is that all right? No need to talk about direction. Okay? Now, I forgot to mention to you just now why people want to use P instead of S. You know, S is the previous one, the MIT stress path parameter. The S is very easy to visualize, but it has one drawback. In terms of constitutive modeling, it has one drawback. And that drawback is that if you look at S and T, the effect of the intermediate principal stress is not considered. So it doesn't appear at all. You know, it doesn't appear at all. So therefore, there is something that is missing from there. So that's the nice thing about P, because you can see P includes, if you want to express it in terms of principal stresses, it will be sigma 1 plus sigma 2 plus sigma 3 over 3. That is the mean normal stress. So the mean normal stress will automatically have the intermediate principal stress taken into account if you express it in principal stress. Whereas S, which is the MIT stress path parameter, will not have this property. Then that's the reason why constitutive modelers love using P instead of S. Okay? So this is the one difference, and P actually is totally independent of direction. It can be, you can just mention it as it's a property of a point, not a direction. Location, yes, not direction. So basically, this is the first stress path parameter, P. The second stress path parameter is actually quite complicated and is called Q. P and Q, S and T. Okay, I just want to come back to this thing about what is the meaning of S and T. You know, when in the early days when you learn soil mechanics, and I'm not going to simplify, you see, because things are looking a bit more complicated now. Suddenly, wow, S and T and then P, and then you look at the Q, is a whole bunch of square root and stuff, and it looks like, wow, I'm getting all lost. Look, let's keep, the most important thing about dealing with stress path is keep the thing simple. All right? And how do you keep it simple? You know, when we are learning soil mechanics in the early days, you remember the shear strength of soil? They will always say this. You plot this is a shear stress, that's the normal stress, you got a failure envelope, and then you draw the Mohr circle. Remember this plot? This must be Very well known to you. Now, what is actually this plot? This plot, I put it to you, is a plot of good guys and bad guys. Yeah, this is the good guy. We say effective stress is good. This is the bad guy. The plot says, the failure envelope says, the more good guy you have, the more bad guys you can handle before you collapse. You know what I mean? So this is the plot of good guy versus bad guy. The same thing with the S&T. When you go to S&T, all right, you realize this is a measure of the shear stress. It is the maximum shear stress. It's the radius of the Mohr circle. This is the position of the center. It tells you how far out is this Mohr circle. So it's a measure of the good guy. It's just another different way of measuring. It's like you go into a gang fight, you know. This group got 11 guys, this group got 10 guys. This group is bound to win. But then this group will say you got more girls. So how you count the girls? Girls count for half. And then the guys who are really big size count for 1.5. You see, it's different ways of measuring. You know what I mean? Huh? Different ways. So this way of measuring a good guy is different from this way of measuring a good guy. This way of measuring a bad guy is different way from this way of measuring a bad guy. I'm not giving you a third way of measuring. The third way of measuring is saying that instead of just taking the average of sigma 1, sigma 2, sigma 3, sigma 1 and sigma 3, we take the average of sigma 1, sigma 2, and sigma 3. There's another way of. So now I'm telling you the third way. Take the total weight of this group versus the total weight of this group. All right. You know, there's a theory in this story about lions and hyena in Africa. You know, the lions have a perpetual battle with the hyena. Sometimes the lion wins and sometimes the hyena wins. And there's a hypothesis that says that if the total weight of the lion is greater than the total weight of the hyena, then the lion will usually win. If the total weight of the hyena is greater than the total weight of the lion, usually the hyena will win. So it's not numbers, it's also something else. So what it tells you is that how you measure this, the way you measure this need not to be a straightforward way. You understand what I mean? But at the end of the day, it's still the good guys versus the bad guys. I don't care what it is. This is still the good guy. So now you've got to find the bad guy. You follow? Okay? And for soil, there's no running away. The bad guy is always something to do with shear stress. Because shear stress is the thing that caused the soil to fail. The good guy is always a measure of effective stress. Because that is the thing that gives soil the strength. You get what I mean? So no matter how complicated the picture seems, just keep this simple thing in your mind and you'll be all right. You know, it's just it's a plot of good guys versus the bad guys. There's nothing to it. Okay? So the question is, how do you measure good guys? Now, this set of stress path parameter is called Cambridge stress path parameter. Okay? And was started by the Cambridge people. And the Cambridge people will tell you a lot of story about how their sense of mechanics is better than the MIT sense of mechanics, and how the story was that Lamb doesn't really understand mechanics and then he screwed up this set of stress. But there's a whole story to it. But never mind, we won't I will tell you the story some other time if you are interested. But essentially, this is the kind of story that comes out. So essentially now, if you look at this has something to do with volumetric change. Right? Volumetric strain. The good guy, he said, hey, the good guy only causes volumetric change. So what is the bad guy supposed to do? So the people said the bad guy should be the guy who causes distortion. Because it is distortion that leads to failure. Pure volumetric change. You know, if I give you a lump of steel like this and I say compress it until it disappears into the blue. I mean, unless you go black hole, you can't do it. And black hole is not soil mechanics. We are a bit far away from it. So essentially in soil, you don't fail by compression. Even if you have an E log P curve, the E log P curve merely says that you yielded a bit, but as the stress increased, the void ratio decreased. But as the void ratio decreased, the stress keeps on increasing. Keeps on increasing. That's not failure. You know what I mean? So basically, so what they say is, the good guy causes only volumetric change. The bad guy must cause only distortion to the shape of the thing. And so they have the way of measuring distortion, which I don't want to go into, but essentially they use energy approach to measure distortion. And so basically you calculate the energy of distortion, the work done into causing the distortion. And that leads you to a definition of the bad guy, which is this. And you can see how formidable it is. That's why before I introduced you to this, I thought I better show you what is the good guy and what is the bad guy. And you realize that actually, if you look carefully enough, it is nothing more than a measure of the shear stress. Why? All the shear stress are here. Right? And you can see this minus this is also some measure of the shear stress. And this minus this is also some measure. It really is nothing more than a measure. It's a question of how you weight each parameter. You know what I mean? It's a weighted way of measuring shear stress. So, okay, I won't go through the details of mathematics of how the energy of distortion is calculated. The details are in the notes. You can actually take a look at it if you want to. But essentially, what comes out is this parameter called Q. Okay, this parameter called Q. And Q is, although it's very complicated, it has some nice feature to it. The nicest feature which I think is that when you think about a triaxial situation, it reduces to just nothing more than the diameter of the Mohr circle. In a triaxial situation, it is nothing more than the diameter of the Mohr circle, which is also the size of the Mohr circle. How do you measure the Mohr circle? By the radius or the diameter? To me, you can do either way. It's fine, no problem. You know? So basically, we now come to the third stress path parameter, and that is the PQ parameter. And I want to tell you this, in all this stress path plot, the bad guy is always the vertical axis. The good guy is always the horizontal axis. Okay? So no matter what it is, just keep your thinking clear to yourself. One is a good guy, one is a bad guy. That's all. Okay? Geomechanics is a story of the good guy and bad guy. Okay? So when we go into more Coulomb, it's the same thing over again. Okay, so basically this group of these two parameters, I've simplified the whole thing quite a bit. These two parameters are called Cambridge stress path parameters, and they were first used by Roscoe, Andrew Schofield, Peter Roth, etc. And that's the reason why it comes to be termed as Cambridge stress path parameter. Now, it so turns out that Q is also independent of direction because Q is derived using energy. Now, you don't have energy, it's not directional. When you say energy, it's energy at which point, strain energy at which point, but it's not directional. You cannot say energy in what X direction versus energy in Y direction. Energy has no direction. So, in the same way, because Q is derived from energy, it also has no direction. Okay? So, both P and Q, the Cambridge stress path parameters, are in a sense independent of direction. These are what you call, in fact, in the study of mechanics, there are special names for this. P is the trace. They call it the trace. I don't know how many of you are familiar with continual mechanics. P is called the trace. And Q is the J2, second stress deviator stress invariant. Okay, so basically there are, but rather than to confuse you even further, let's just call it the good guy and the bad guy. Okay? Okay, now, I just want to go push on a little bit into triaxial test situation. Because a lot of the thing that you'll be doing with is triaxial test. Oh, talking about triaxial test, I have got a whole series of problems which I work out on GeoFEA, which I've generated the mesh. So don't worry, you don't need to generate the mesh. Actually, I also don't know how to generate the mesh. Although I said the program was developed by me and my students, but they developed the user interface, and I'm very poor in finding my way around all those things. But I think after a while, you will probably find your way better than I do. But the main thing in the exercise is not to let you generate the mesh, but I give you the mesh, you change the material property, and you rerun that. Then you'll be able to see by assigning different material property to the problem, and the mesh I give you is actually nothing more than a triaxial test. Then you will see how a triaxial test come out looking like with different material property. And that is the first step to think. To me, that is a very nice, simple first step that all engineers starting with FEM should actually do, because you have to explore the material first, the material model first, using a simple problem that you know very well. And what is simpler than a triaxial test? You know what I mean? So basically, to me, this is something that very few people ever done, in practice. For some reason, engineers don't say, hey, why don't I do a triaxial test and see what the thing looks like? Is it giving me sensible result or non-sensible result? To me, if you can't even get sensible result out of a triaxial test, why bother with a deep excavation? Why bother with a tunnel? You know what I mean? You cannot win already. So the first thing is to make sure that the result coming out of the triaxial test, you know how to set the parameter in such a way that you're getting sensible results. And when you change the parameter, the result change also in a sensible way. That is very important. So I hope that, because the emphasis on this course is on constitutive modeling, so I hope that by giving you a simple set of parameters, say for the more Coulomb and for the modified chem clay, and then you just change various things, and then you can see how the result change, how the stress strain curve change, how the stress path change. Then you go out there, you got an idea. When I do something, this is what should happen with that model. You know what I mean? Okay, so this is how we are going to do it on the. That in essence is roughly what the assignment. So the assignment shouldn't require you to. If you want to generate your own mesh, I will not stop you. Okay, but I will give you the mesh. It's not the fastest mesh. To me, the mesh is an overkill mesh. Overkill because it's too complicated, too many elements. For a triaxial test, ideal triaxial test, you should only have some. You only need, in theory, only 2 or 3 elements is needed. 2 to 4 elements is all that's needed. But this thing has got probably like a few hundred elements we saw, right? I think it's over, but it wasn't generated by me. It was generated by one of the engineers at the company. So anyway, it's okay. So we just make the computer work a bit harder. You know? So you don't have to generate the mesh. But if you want to generate a mesh, you can generate a mesh. Not an issue. Okay? But the point of this course is not to get you generating mesh. That is not the idea. The idea is to let you explore material properties. Okay? So basically, triaxial condition. Now, this is a very important thing. The important thing I want to emphasize is keep your thinking simple with respect to stress path parameter. The x-axis is always the good guy. And it has always something to do with a measure of effective stress. The y-axis is always the bad guy. And it's a measure of the shear stress. That's all there is. All right? How you weight it, what component you consider, what you don't, that's different thing. But that is, the intent is the same. The intent is the same. Right? Yeah. This one? No. Okay. This is how the guy draw the failure envelope. He's drawing a failure envelope. What happened is that actually this line was not drawn based on this. What happened is that this is a failure envelope that was deduced from the Mohr circle. What happened is that he first do this, the standard Mohr circle. He's got 3 tests, right? He got an effective stress Mohr circle. Now, when you put the 3 Mohr circle together, very often, you ever seen enough of those things, the 3 Mohr circle will not be aligned perfectly. So, you either choose to put your line this way a little bit to fit the second and the third circle, or you choose to tilt the line this way to fit the first and the second circle, or you choose to fit the line through the first and the third circle but cut through the second circle, or whatever it is, something, it will not fit perfectly. So the guy actually then fitted the line to the Mohr circle first, deduced the angle of friction and the cohesion, and then used that to deduce this particular line. So you can see that there's some discrepancy there. There's some discrepancy there. But it is not unreasonable sometimes to expect real soil to shoot above the U surface. Is not unreasonable, because although we say Mohr Coulomb model should not allow the soil to go past, but the soil doesn't understand Mohr Coulomb. He only understands his own behavior. So therefore, you know what I mean? He will go his own way. So therefore, sometimes you'll get a bit of accident. And this is part and parcel of the imperfection of soil models. And it's not just Mohr Coulomb. Most real soil model will have this imperfection. So to me, if you ask me about this, I would say this kind of magnitude of discrepancy, I'll say I'm okay with it. Actually, I'm okay with it. But I suspect the line was actually deduced from the Mohr circle. Because the guy has to make sure that the 2 lines are consistent. And I think that he doesn't know how to do this, so he can only do this. The engineer will only do this and then use this to deduce that. Okay, we now go to a triaxial test. Why is it triaxial test? Because as I mentioned to you, in a triaxial test, it turns out that it turns out that the definition of P and Q becomes very, very simple. Okay, what is the condition of a triaxial test? The triaxial test is the axisymmetric, is a circular specimen, right? Circular specimen. So you can say that the two horizontal stress are the same, is equal to 1, the radial stress, sigma r. Right? Two orthogonal directions are the same. Then the vertical stress is actually the axial stress. You're pressing it this way, right? Axial stress. And then the shear stress are all 0. There's no shear stress. Agree? Okay. So the moment you feed all this in, straight away, you can easily, very quickly show that P is equals to sigma A plus 2 sigma R divided by 3. Now, you can in fact treat this as the major principal stress. So sigma 1 plus 2 sigma 3 divided by 3. Because they are in fact the major and the minor principal stress. Q is then equals to sigma A minus sigma R, or sigma 1 minus sigma 3, because sigma A is also the major principal stress, sigma 1. Sigma R is also the minor principal stress, sigma 3. So therefore Q is equals to the difference between the major and the minor principal stress, which in fact is the diameter of the Mohr circle. Which is why I told you just now that the nice thing about this guy is that when you specialize it to a triaxial situation, it is nothing more than the diameter of the Mohr circle. So this is the diameter of the Mohr circle, that's the radius of the Mohr circle, that's the shear stress. Basically, they are all measures of the shear stress. You know what I mean? And that's the reason why I said that is, all bad guys are related to a shear stress. Some way of quantifying, measuring the shear stress. Okay? So the higher shear stress means shear failure is more likely, and that is bad news. Okay? Just this to me is one of the most important slides, because once you see this, then the rest is actually very straightforward. There's nothing to it. Okay? Right, in a conventional triaxial compression test, okay, you'll notice that in fact the lateral stress, which is the radial stress, is kept constant. So therefore, as a result, you can say that the delta sigma r is 0, while the axial stress is increased. Okay? Now you can deduce incrementally from the triaxial test. The incremental form is the change in P is equals to the change in sigma A plus 2 times the change in sigma R divided by 3. Change in Q is equals to change in sigma A minus change in sigma R. So this is just deduced straightforwardly from these two equations. Just deduce from this by just putting delta in front. Okay? So essentially you can deduce the change in P and change in Q. And if you furthermore assign delta sigma R to be 0 in a standard triaxial compression test, okay, then what you then end up with is this is 0, that is 0. So then delta P is equals to delta sigma A over 3. Delta Q is delta sigma A. Agree? So now I take the ratio of these two. If you take the ratio of these two, the ratio of these two is 3. So therefore the PQ stress path in a triaxial, the total stress path, the PQ total stress path will always have a gradient of 3. And so it will be a straight line with the gradient of 3. And I think I don't have to draw it here because I think it's over here. Alright. TSP over here refers to total stress path. TSP, total stress path. Okay? So basically, the total stress path in a conventional triaxial test is a straight line with a gradient of 3. So if you ever get a question from the quiz and say, what is the stress path in a total stress path in a conventional triaxial, or deduce a total stress path, just close one eye and draw a straight line and just indicate 3. Okay? If that comes out, then it's a gift question. Okay? So anyway, this is the total stress path. Okay? Now you can also define a set of effective stress parameter as follows, and the effective stress, the effective P or P dash is equals to sigma x dash plus sigma y dash plus sigma z dash over 3. And this is called the mean effective stress, the average effective stress. And you realize the average effective stress is also still a measure of effective stress. Correct? It's just that you also take into account the other components of effective stress, major, minor, intermediate. So it's also a measure of the effective stress. Now Q dash is equals to this. And I can tell you without having to derive it, that Q dash is equals to Q. Alright? In a triaxial condition, Q is the diameter of the Morse circle. The diameter of the total stress circle is the same as the diameter of the effective stress circle. So they have to be the same. And you think about it, Q is a measure of shear stress. There's no such thing as total shear stress or effective shear stress. Shear stress is shear stress, because water will not take shear stress. No matter how you measure it, you will not be able to take any shear stress. And you can easily prove that Q dash is equals to Q. So I won't bother to work through the mathematics. I'll just kind of take it that you accepted it, and Q dash is equals to Q. But in fact, if you want to do it, it's very easy. This is equals to this is equal to this. You just substitute it in, Q dash is equals to Q. Okay? So essentially, T dash equals to T, tau dash equals to tau, Q dash equals to Q are all statements that water takes no shear stress. Alright? The soil skeleton is the one that is taking all the shear stress. So the stresses that cause any distortion, any kind of shearing, must be taken entirely by the soil skeleton. Okay? So this kind of set the scene for us. So P dash is equals to that, Q dash is equals to Q, and now we can try to relate P dash and P dash and P, because we know that P dash is equals to sigma A dash plus 2 sigma R dash over 3. But we know sigma A dash is sigma A minus U. Sigma R dash equals to sigma R minus U. Right? So if you just substitute this whole lot into here, you realize you will immediately come to the conclusion that P dash is equals to P minus U. So P actually obeys the effective stress principle. Effective P equals to total P minus pore water pressure. So the good guys are affected by the pore. It's a double bad news. The good guys are affected by the pore water pressure. The bad guys are not affected by the pore water. So the good guys are fighting under handicap. Yeah, because higher pore water pressure means less good guy. You know what I mean? Okay, so similarly, you can express everything in terms of incremental form. Delta P dash equals to delta P minus U. Delta Q dash equals to delta Q. There's no difference. Okay, now I want to move on a bit and take a look at this change in delta P dash. Change in delta P dash. Now, we can say that volumetric strain is equals to P divided by K, total stress. But it can also be expressed, the volumetric strain of the soil skeleton is equals to epsilon V, is equals to P dash divided by K dash. So you can actually say that from the point of view of the soil skeleton, change in the volumetric strain is equals to change in the P dash divided by K dash. Where K dash is the effective bulk modulus. Effective bulk modulus. Okay? Now, the important thing is this, what is the condition for an undrained test? In the undrained test, can the soil skeleton change volume? You cannot change because the water is not moving in, not moving out. So the volume has to be constant, right? So delta epsilon V is 0. There's no change in volume. So if there's no change in volume here, this part is 0, and therefore delta P dash must be 0. So therefore, this means that in the context of an undrained test, P dash cannot change. Alright? And for a linear elastic material, this means that if P dash cannot change, so you just imagine now, you look at this. Now, on this plot, you want to have a stress path, effective stress path, such that the x coordinate doesn't change. What does the stress path look like? It's a vertical straight line. That's the only path that will give you no change in P dash. Agree? That is the only path that will give you no change in P. Therefore, for a linear elastic material, the undrained stress path in terms of PQ, stress path parameter, is always a vertical straight line. It's always a vertical straight line. We know that the total stress path is a straight line with a gradient of 3 to 1. The effective stress path is always a vertical straight line. Okay? So now we can deduce the two straight lines. Immediately we have already deduced the stress path for triaxial test, for undrained triaxial test, for total stress path, and the effective stress path. And this shows you the two stress path. on the right side, TSP, this is the total stress path. On the left side, this is the effective stress path. Now, we look at it, these two stress paths represents the stress changes throughout the test. So the question is then, how do I relate at any one point of time or at any point of the test, where is the effective stress point and where is the total stress point? Very simple. At any point of the test, one thing we have to remember, Q dash equals to Q, or the Q is always the same. You know what I mean? At any point of the test, Q is always the same. So therefore, supposing I have a point here, A, this point is on the total stress path. I want to locate the corresponding effective stress state for this point. What I have to do is just to look across, take a horizontal straight line, cut across. This point here will be the effective stress state for this particular moment, this point of the test. And why is that so? Because Q for here is this, the vertical coordinate. The vertical coordinate. This must be the same as this. The two must be the same. So therefore, you take any pair of points on the vertical line cutting across these two lines, those are the total and the effective stress points. And then what is the offset? The offset, of course, is the excess pore water pressure. P dash minus P is the excess pore water pressure, because that was what we have just now. P dash equals to P minus U, or P minus P dash is equals to U. That is the excess pore water pressure. So therefore, we are now able to deduce that, supposing this is the point of the test that we are considering, this is the total stress state, total P, this is effective P, and this is the excess pore pressure. This is the excess pore water pressure. Now this is a very important thing because we will be coming back to use it. And it so turns out that the collapse of the nickel highway in 2004, and the thing about method A, method B, turns out to be very, very intimately related to this. Okay, and it's a pity that a lot of engineers in Singapore still running around not understanding all these situations. So I hope we all can learn a lesson from it and that we can avoid some of these things. So essentially, you can say that the lateral offset between the total stress and the effective stress path at any point of the test is actually the excess pore water pressure. Is that all right? That is actually the excess pore water pressure. Okay? Now, you can immediately deduce from here. This is the geometry. The geometry of this is very straightforward. This is a gradient with 3 to 1. This is Q, but your starting Q is 0. So this is also equals to delta Q, right? Change in Q, because your starting Q is 0. So your change in Q is equals to Q. So this is delta Q. So Q dash equals to Q equals to delta Q. So this is delta Q. So now if I say what is the ratio of delta U to delta Q? 1/3. Because of the geometry of the triangle with a gradient of 3 to 1. Agree? Okay? Because you got a straight line here. Straight line here equals to 3 to 1. So therefore this distance divided by this distance must be 3 to 1. Alright? So the horizontal distance must be equal to the vertical distance divided by 3. So delta U equals to delta Q over 3. Alright? Delta U equals to delta Q over 3. Okay, now, we are now in a position to take a look at Skempton's pore pressure parameter. And I think, at first I wanted to skip this part, but I thought that actually this part is very closely related to how you pick your model. The point at the end of the day, how you pick your model. And why the nickel highway collapsed. Why they picked the wrong model and why the nickel highway collapsed. I think this is very important. So I thought maybe I'll just go do a little bit more on good old Skempton. Okay?